Imagine looking up at the night sky on a clear evening. You see thousands of glittering stars, distant galaxies, and the glowing band of the Milky Way stretching overhead. It's a breathtaking view, one that feels complete and full, but here's the astonishing truth. Everything you can see with your eyes, everything our most powerful telescopes can observe, only accounts for about half of the normal matter that should be out there. The rest is missing. For decades, astronomers have grappled with this cosmic puzzle, a mystery as profound as it is invisible. Known as the missing baryon problem, it challenges our very understanding of the universe's structure and history. If the Big Bang theory is correct, there should be far more ordinary matter, protons, neutrons, and electrons spread throughout the cosmos. But where did it go? How could something so fundamental simply vanish without a trace? This isn't just a small gap in our knowledge. It's a gaping hole in the cosmic inventory, one that has pushed scientists to the edges of innovation and curiosity. We're not talking about dark matter or dark energy here. Those are separate enigmas altogether. This is about the stuff you and I are made of, the atoms that form planets, stars, and life itself. And the fact that half of it is unaccounted for means our picture of the universe is, quite literally, only half complete. Yet instead of discouraging researchers, this mystery has ignited one of the most thrilling detective stories in modern astronomy. A pursuit that has led to astonishing breakthroughs and unexpected discoveries. In this video, we're embarking on a journey to explore 25 incredible clues that scientists are using to solve the missing baryon problem. From vast, faint webs of gas hiding between galaxies to high-energy particles streaking across the cosmos, each clue brings us closer to understanding where the missing matter has been hiding. This is a story of human ingenuity, of technology piercing the veil of the invisible, and of a universe far more complex and wondrous than we ever imagined. So settle in and open your mind. We're about to dive into the secrets of the cosmos, tracing the faint signals and subtle echoes of matter that has eluded us for generations. The answers are out there, waiting to be found. To understand just how much of the universe is missing, we have to wind the cosmic clock all the way back to the very beginning. In the first few minutes after the Big Bang, the entire universe was an unimaginably hot, dense soup of fundamental particles. Protons and neutrons buzzed about in a frenzy, and during this brief, searing window, the first atomic nuclei were forged. This process, known as Bang Nucleosynthesis, was the universe's first and largest-scale atomic cook-off. It primarily produced the two simplest elements, vast amounts of hydrogen, the fuel for all future stars, and a significant portion of helium. Crucially, the physics governing this ancient nuclear fusion is exquisitely simple and well understood. It relies on fundamental constants like the strength of gravity and the nuclear forces, which we can measure with incredible precision in laboratories right here on Earth. Because the rules are so basic and the environment was so uniform, cosmologists can calculate with a high degree of certainty exactly how much baryonic matter, that's the formal term for ordinary protons and neutrons, should have been created during those first 3 minutes. The calculations point to a very specific amount. If you were to take a cosmic inventory, adding up all the normal matter that should be dispersed across the entirety of space, this is the number you'd expect to find. It becomes our baseline, our cosmic expectation. For a long time, astronomers assumed this matter was all accounted for in the things we could easily see, the glittering galaxies, the glowing nebulae, and the stars themselves. But when they started adding it all up, the numbers came up short, dramatically short. The total mass locked in stars, the gas within galaxies, and all the visible dust only accounts for a fraction of that primordial prediction. This discrepancy isn't a small rounding error. It's a gaping hole, suggesting that over half of all the ordinary matter in the universe is simply not where we thought it would be. This is the very heart of the mystery. Big Bang Nucleosynthesis gives us the should-be number, and our telescopes show us the what we see number. The difference between them is the missing baryon problem in a nutshell. It tells us that our search isn't for some exotic, unknown substance, but for the very same atoms we're made of, hiding in plain sight, or more accurately, hiding in the dark. This reliable yardstick from the dawn of time is our first and most crucial clue, the undeniable proof that something is out there waiting to be found. So where did astronomers begin their search for this missing matter? They started with the obvious, with everything that shines. For centuries, the primary way we've understood the universe is by collecting its light. We point our telescopes at the sky and we see stars, galaxies, and nebulae islands of light in the cosmic dark. It seems only logical that this is where the majority of the universe's mass should be concentrated. To put this assumption to the test, scientists embarked on the most ambitious cosmic accounting project imaginable, a precise inventory of all the luminous matter in the observable universe. This isn't a simple head count, it's an incredibly complex process of measuring distances, brightness, and masses across billions of individual objects. The cornerstone of this effort has been monumental projects like the Sloan Digital Sky Survey. Imagine a telescope meticulously scanning the heavens night after night, not for a few years but for decades. It has mapped over a third of the entire sky, cataloging the precise positions and colors of hundreds of millions of distinct celestial objects. From this immense catalog, astronomers can determine a galaxy's distance by how much its light has been stretched redward by the expansion of the universe. They can estimate its mass by measuring how fast it rotates, or by studying how its gravity bends the light from more distant galaxies behind it. For stars within our own galaxy, we can calculate their mass based on their color and brightness. It's a painstaking statistical process, building a cosmic census one day to point at a time. The numbers that emerge from this inventory are, to be frank, mind-numbingly enormous. The total mass of stars alone adds up to hundreds of billions of times the mass of our own sun, spread across a similar number of galaxies. When you add in all the vast clouds of gas and dust that swirl within those galaxies, the raw material for future stars, the figure becomes even more staggering. It feels like it should be enough that this brilliant tapestry of light must constitute the bulk of creation. And yet, when cosmologists take this grand total and compare it to the expected amount of matter from Big Bang nucleosynthesis, the result is a profound shock. All the stars, all the galaxies, all the glowing gas we can see, it accounts for less than half of the ordinary matter that was created. This realization was a pivotal moment in astronomy. The shortfall wasn't just a small discrepancy, it was a gap of epic proportions. It meant that the universe as we saw it through our most powerful telescopes was merely the tip of a vast, invisible iceberg. The galaxies were not isolated cities in an empty countryside. They were likely just the brightest nodes embedded within a much larger, unseen structure. This inventory, while coming up short, gave the mystery its precise scale. It defined the size of the hole we needed to fill. We weren't just missing a few stray planets or faint stars. We were missing an amount of matter equivalent to all the visible galaxies put together, and then some. The search was no longer about confirming a theory. It was about finding an entire second universe of material that had somehow remained hidden in plain sight. But if the galaxies themselves hold only a fraction of the universe's normal matter, where could the rest possibly be? To answer that, we have to confront an even deeper cosmic mystery, one that doesn't just hide matter but actually dictates where it can and cannot go. This brings us to our third clue, which involves a substance that is fundamentally different from the atoms we're made of, yet whose gravitational influence is absolutely inescapable: dark matter. Now, it's vital to clarify that dark matter is not the missing baryons we're searching for. Dark matter is something else entirely, a mysterious substance that does not emit, absorb, or reflect any light, making it completely invisible to our telescopes. We only know it exists because of its profound gravitational pull on the things we can see. Think of it like this. When astronomers measured how fast stars orbit the center of their galaxies, they made a startling discovery. The stars on the outer edges were moving far too quickly. Based on the visible mass of all the stars and gas in the galaxy, their tremendous speed should have sent them flying off into intergalactic space. The fact that they remain bound to their galaxies means there must be a huge amount of additional mass, an enormous invisible halo of dark matter, whose gravity is the only thing holding these stellar cities together. This effect isn't just limited to single galaxies. We see the gravitational fingerprint of dark matter everywhere on the largest scales imaginable, warping the fabric of space-time itself. This invisible scaffolding is the true architecture of the cosmos. In the early universe, slight density fluctuations in the dark matter began to collapse under their own gravity, forming vast gravitational wells. It was into these wells that ordinary baryonic matter, the hydrogen and helium gas, flowed. The dark matter provided the skeletal structure, and the normal matter followed, clumping together to eventually form the very first stars and galaxies. So the distribution of galaxies we see today isn't random. They are all strung along an invisible network of dark matter filaments, a cosmic web that spans the entire universe. The glittering galaxies are just the brightest knots where this web is densest. This understanding is our crucial third clue because it completely changes the search image for our missing baryons. It tells us that normal matter is not distributed evenly throughout the void. Instead, it's been channeled and organized by the irresistible gravitational pull of dark matter. Therefore, the missing atoms aren't likely to be floating alone in the desolate emptiness between galactic clusters. They are almost certainly still associated with this massive cosmic scaffolding. They are hiding in the vast, diffuse filaments of the web itself, in the moderately dense regions that never quite collapse to form brilliant galaxies, or in enormous, faint halos enveloping entire clusters of galaxies. The dark matter gives us a map, a gravitational blueprint that tells us where to look for the universe's hidden ordinary matter. We just needed to develop the tools to see it. So if the dark matter provides a cosmic map pointing toward the vast filaments of the web, what exactly are we supposed to be looking for in those empty corridors? The leading suspect for hiding such an enormous amount of material is a form of matter so diffuse and energetic that it's practically invisible to our conventional eyes, the warm, hot intergalactic medium, or WHIM. The name itself sounds like something from a cosmic weather report, but it describes one of the most extreme environments in the universe. This isn't the cold, dark void we often imagine between galaxies. Instead, it's a seething ocean of superheated gas with temperatures ranging from 100,000 to tens of millions of degrees Celsius. How did this gas get so incredibly hot? The answer lies in the violent history of the cosmic web itself. As gravity pulled matter into the filaments and knots of dark matter, ordinary gas flowing into these structures didn't just fall gently, it crashed. Think of it like a gigantic cosmic traffic jam. When gas streams from different directions collided within these narrow filamentary highways, the resulting shock waves sent ripples of tremendous energy through it, heating it to these phenomenal temperatures. It's a process that has been ongoing for billions of years, with the endless pull of gravity continuously feeding and re-energizing this vast intergalactic furnace. This extreme heat is precisely what has made the WHIM so devilishly difficult to find. A cloud of cold gas would reveal itself by absorbing the light from bright objects behind it, like a dark silhouette against a spotlight. But gas heated to hundreds of thousands of degrees behaves entirely differently. the atoms within it become ionized, meaning they are stripped of their electrons, leaving behind a chaotic soup of naked atomic nuclei and free-flying electrons. This ionized plasma doesn't absorb light in neat, recognizable patterns like cooler gas. It instead glows very faintly in high-energy X-ray light. But that glow is so incredibly faint, spread across such immense volumes of space, that it's drowned out by the brilliant point sources of X-rays coming from things like black holes and neutron stars. It would be like trying to hear a single whispered conversation across the roar of a stadium crowd. For a long time, our telescopes simply weren't sensitive enough to pick up this whisper-thin signal against the noisy background of the universe. Yet, the theory is compelling because the numbers add up. The sheer volume of space occupied by these web-like filaments is so colossal that even this incredibly thin, hot gas, if it's really there, could easily account for all the missing baryonic matter and finally close the cosmic budget. Hunting for this incredibly faint, superheated gas required a completely new approach to astronomy. We couldn't simply point a telescope and take a picture. We had to become cosmic detectives, looking for subtle clues left behind in the light of the universe's most brilliant beacons. This brings us to our fifth clue, the ingenious use of X-ray and ultraviolet observations to catch the warm, hot intergalactic medium in the act. The strategy relies on a classic technique of physics, but applies it on a truly grand scale. Instead of trying to see the WHIM glow directly against the dark background of space, astronomers use incredibly bright, distant objects as backlights. The most powerful of these cosmic lamps are quasars, supermassive black holes at the centers of ancient galaxies that are actively devouring enormous amounts of material. This process unleashes a torrent of radiation, blazing across the entire electromagnetic spectrum from radio waves to gamma rays, creating the most luminous single objects in the entire universe. As this intense beam of light travels across billions of light years towards our telescopes, it doesn't journey through a perfect vacuum. It passes through the vast, invisible structures of the cosmic web. If that web is indeed filled with the hot, ionized gas of the WHIM, then the atoms within that gas should leave a mark on the quasar's light. Specifically, elements like oxygen, neon, and nitrogen, which have been stripped of some of their electrons by the intense heat, will absorb light at very specific, characteristic wavelength. It's a concept similar to holding a colored filter in front of a bright light. Certain colors are absorbed, revealing the fingerprint of the filter's material. In this case, the filter is a filament of million-degree gas millions of light years across, and the fingerprint is a tiny, specific dip in the spectrum of the quasar's brilliant light. This is where our most powerful space observatories come into play. The Chandra X-ray Observatory is designed to see the high-energy universe. Its delicate instruments can dissect the X-ray light from a quasar, searching for those telltale absorption lines caused by highly ionized oxygen atoms, atoms that have been stripped of most of their electrons, a state that only occurs in environments as intensely hot as the predicted WHIM. Simultaneously, the Hubble Space Telescope, though often celebrated for its stunning visible light images, is also a powerful tool for ultraviolet astronomy. Hubble's sensitive spectrographs can detect the absorption signatures of slightly cooler but still immensely hot gas in the ultraviolet part of the spectrum. By combining the data from these two great observatories, astronomers can effectively take a core sample of the cosmic web, analyzing the material embedded within the vast filaments that connect the galaxies. Each successful detection, each tiny dip in a quasar's spectrum, is like finding a single glowing needle in a haystack the size of a galaxy. It's painstaking, meticulous work, but these faint spectral lines are the first direct fingerprints of the universe's missing matter, confirming that it has been hiding in the hot, sparse plasma that fills the spaces between everything we see. But detecting these faint spectral lines is an incredibly challenging task. often requiring immense amounts of observation time on our most prized telescopes for what might be just a handful of promising detections. To truly map the vast, invisible structure of the cosmic web, we needed a method that could work on a grander scale, one that didn't rely on the rare, perfect alignment of a distant quasar. This need led to the development of one of the most powerful and ingenious tools in modern cosmology, the Sunyaev-Zel'dovich Effect. The principle behind it is as brilliant as it is complex, turning the entire universe's oldest light into a backlight for finding hidden matter. To understand how it works, we have to go back to the very beginning, to the afterglow of the Big Bang itself. About 380,000 years after the universe was born, it had expanded and cooled enough for protons and electrons to combine into neutral hydrogen atoms. At that moment, for the first time, light could travel freely through space without constantly bumping into charged particles. This first flash of light, now stretched and cooled by the expansion of the universe over 13 billion years, still fills every cubic centimeter of space today. We know it as the cosmic microwave background, a nearly uniform sea of microwave radiation that is the oldest fossil we can observe. It is the ultimate cosmic background, a perfect snapshot of the infant universe. Now imagine this ancient light, having traveled for over 13 billion years on a perfectly straight path, finally approaching our telescopes. But on its long journey, it must pass through the large-scale structures of the modern universe, the massive galaxy clusters and the vast filaments of the cosmic web. If those structures are filled with the seething, ionized gas of the WHIM, a fascinating interaction occurs. The hot, energetic electrons that are flying about in that superheated plasma crash into the low-energy photons of the cosmic microwave background. When this collision happens, the photon gets a significant energy boost, much like a ping-pong ball being hit by a fast-moving tennis ball. This process, known as inverse Compton scattering, subtly changes the properties of that ancient light. From our perspective, this creates a very specific and detectable signature. The cosmic microwave background has a very specific blackbody spectrum, but as its light passes through a cloud of hot electrons, that spectrum gets distorted. The number of low-energy photons in the microwave range appears to decrease slightly, while the number of higher-energy photons increases. It's an incredibly subtle effect, a change in temperature on the order of 1 part in 10,000. But it is a change that modern radio telescopes are exquisitely sensitive enough to measure. By scanning the sky and creating incredibly detailed maps of these tiny temperature fluctuations in the cosmic microwave background, astronomers can essentially see the shadows of these immense hot gas structures. Every slight dip in the temperature map isn't a hole, it's a signpost pointing directly to a massive reservoir of incredibly hot, diffuse plasma. The true power of the Sunyaev-Zel'dovich effect lies in its uniformity. Unlike the quasar method, which requires a brilliant but rare beacon to be perfectly positioned behind the gas we want to study, this technique uses a backlight that is everywhere at once. It allows astronomers to conduct blind surveys of the sky, systematically searching for these telltale distortions and building a three-dimensional map of the warm-hot intergalactic medium's distribution. It has been instrumental in confirming the presence of enormous amounts of hot gas, not just within the dense cores of giant galaxy clusters, but also stretching out along the filamentary threads that connect them. This method doesn't just find a few needles in the haystack, it helps us finally see the size and shape of the haystack itself, revealing a hidden architecture of ordinary matter that has eluded us for decades. While the Sunyaev-Zel'dovich effect uses the oldest light in the universe as a backlight, another technique allows us to read a fossilized imprint left in the very structure of matter itself, an echo from a time when the cosmos was a seething, roaring chaos. This brings us to a profound and elegant clue known as Baryon acoustic oscillations. To understand what these are, we have to journey back to the universe's first few 100,000 years, a period that was anything but silent. In this incredibly dense and hot primordial soup, ordinary matter existed as a plasma of protons and electrons, while light, in the form of photons, was hopelessly tangled within it. These photons couldn't travel any meaningful distance without crashing into a charged particle, creating a thick, opaque fog. But this mixture had a fascinating property. The tremendous pressure from the intense radiation of the photons pushed outward, while the relentless pull of gravity from the dark matter tried to pull the plasma inward. This push and pull created a series of powerful pressure waves, effectively sound waves, that rippled outward through the young universe. These weren't gentle ripples, they were the most massive sonic booms in existence, propagating at a significant fraction of the speed of light. For nearly 400,000 years, these waves spread through the cosmic medium, with the photons acting like a fluid, carrying the baryons along with them in their expansion. Then, in a cosmic instant, everything changed. As the universe expanded and cooled, it finally reached a temperature where electrons could combine with protons to form stable, neutral hydrogen atoms. In what cosmologists call recombination, the fog suddenly cleared. The photons, no longer bouncing off free electrons, were suddenly set free, streaming across the universe to eventually become the cosmic microwave background we detect today. But crucially, at the exact moment this happened, the pressure waves stopped. The sound waves froze in place, their final wavefront effectively etched into the distribution of matter. The baryons that had been carried to the edge of that wave formed a slightly denser shell around the point of origin. This process happened everywhere at once, all across the universe. The result was that matter wasn't distributed completely randomly. There was a subtle preference for galaxies to form at a specific scale, the distance that sound could travel in those first 400,000 years. This distance, about 500 million light-years across, became a permanent, standard ruler imprinted on the cosmos. For billions of years, as the universe expanded, this preferred scale expanded with it, stretching that original distance to nearly 500 million light-years today. This is where modern cosmology performs its magic. By conducting enormous galaxy redshift surveys, like the Sloan Digital Sky Survey or the Dark Energy Survey, astronomers can map the three-dimensional positions of millions of galaxies. When they statistically analyze these maps, they can detect this subtle signal, a slight statistical excess of galaxy pairs separated by that specific 500 million light-year distance. It's like hearing a faint, persistent echo of the Big Bang itself in the large-scale structure of the universe. Measuring this BAO signal is incredibly powerful because it provides a direct way to measure the expansion history of the universe, and more importantly for our mystery, it gives us another way to count baryons. The strength and clarity of this acoustic oscillation signal depend directly on how much ordinary matter was present to be pushed by those primordial sound waves. If there were very few baryons, the waves would have been weak and the signal faint. A strong, clear BAO signal tells us that a significant amount of baryonic matter must have been present to participate in this cosmic symphony. When cosmologists measure this signal, the amount of baryons it implies aligns perfectly with the predictions from Big Bang Nucleosynthesis. It acts as a completely independent check, confirming that the total budget of ordinary matter is exactly what we thought it should be. The BAO signal doesn't tell us where the missing matter is hiding, but it powerfully confirms that it absolutely must be out there somewhere, because its gravitational signature is permanently written into the clustered pattern of the galaxies we can see. It's the universe's own accounting ledger, and the numbers match. If we want to take a true census of the universe's hidden gas, we need a method that can probe vast stretches of cosmic time and space, far beyond the reach of even our most powerful direct imaging. For this, astronomers turn to the universe's ultimate natural lighthouses, quasars. These are not merely bright objects, they are the most violently energetic phenomena in the cosmos. A quasar is the blazingly bright core of a distant galaxy. powered by a supermassive black hole that is actively feasting on an enormous disk of surrounding gas and dust. The gravitational energy released in this frantic feeding process is so immense that it can outshine the combined light of every single star in its host galaxy, making a quasar visible clear across the observable universe. This unbelievable brightness is what makes them the perfect tool for our search. A quasar's light is a piercing beam that shines through the dark, silent corridors between galaxies. As this torrent of light travels for billions of years on its journey to our telescopes, it doesn't move through a perfect vacuum. It inevitably passes through countless clouds and filaments of gas, the very reservoirs where our missing baryons are thought to be hiding. And when it does, that gas leaves its mark. The key to reading these marks lies in a fundamental principle of physics. Every element in the universe absorbs light at a unique set of wavelengths, its own atomic fingerprint. To detect this, astronomers don't just take a picture of the quasar. They use an instrument called a spectrograph to break its light apart into a full rainbow spectrum, a detailed barcode of its composition and journey. What they find is astonishing. Instead of a smooth, clean spectrum, they see a forest of hundreds, sometimes thousands, of dark absorption lines. Each one of these tiny dips in the light is a shadow, cast by a specific cloud of gas at a specific point along the line of sight. It is a fossil record of every structure the quasar's light has passed through on its multi-billion-year journey to Earth. By meticulously analyzing this Lyman alpha forest, named for a specific absorption line of hydrogen, astronomers can do something extraordinary. They can reconstruct a core sample of the universe's large-scale structure. Each absorption line tells them not only what the cloud is made of, usually hydrogen, the most abundant element, but also how ionized it is, its temperature, and crucially, its distance from us. The amount the cloud's light is redshifted reveals how long the light has been traveling, and therefore how far away the cloud is. A single quasar spectrum provides a one-dimensional core sample, a narrow straw pushed through the cosmic web. But by pointing our telescopes at thousands of quasars spread across the sky, we can build up a stunning three-dimensional map of this invisible gas, charting its distribution and density from the relatively nearby universe all the way back to when galaxies were first beginning to form. This intricate forest of lines is more than just a map. It's a direct measure of the total amount of ordinary matter strewn across intergalactic space. By counting the lines and measuring their depth, cosmologists can literally add up the baryonic content of the universe. The results from these quasar censuses have been revelatory. They show that a significant portion of the universe's normal matter does indeed reside in this diffuse, gaseous form, spread throughout the vast cosmic web. It confirms that the missing atoms aren't in some strange or exotic form. They are simply hydrogen, the universe's most basic building block, hidden in plain sight because it is too diffuse and too hot to glow on its own, yet perfectly visible when backlit by the most powerful beacons in creation. Of all the fingerprints hidden in a quasar's rainbow spectrum, one specific set of lines holds a uniquely powerful key to unlocking the mystery. These are the Lyman alpha absorption lines, and their sheer number and complexity have earned them a beautiful and fitting name, the Lyman alpha forest. Each dark line in this dense, intricate thicket is a shadow cast by a single cloud of neutral hydrogen gas, the most fundamental substance in the universe. As the brilliant light from a distant quasar travels across the cosmos, it passes through countless filaments and halos of this primordial gas. Whenever the light encounters a cloud of neutral hydrogen, the atoms within it are perfectly tuned to absorb light at one very specific wavelength in the ultraviolet part of the spectrum, the Lyman alpha line. This simple, predictable interaction, repeated across billions of light years, creates a stunningly complex record of everything the light has passed through. The true magic, however, lies not in the absorption itself, but in the expansion of the universe. Each of these hydrogen clouds is at a different distance from us. Because the universe is stretching, the light we receive from each cloud has been stretched as well. Its wavelength shifted redward in a phenomenon we call redshift. A cloud that is relatively nearby will have its Lyman alpha line shifted only a little, perhaps still within the ultraviolet range. But a cloud that is extremely far away, whose light has been traveling for billions of years, will have its absorption line stretched or redshifted all the way into the visible part of the spectrum. The result is a quasar spectrum that looks like it's been combed with 1,000 fine-toothed rakes. The entire spectrum, from the ultraviolet to the visible, is filled with these absorption lines, each one representing a different cloud at a different moment in cosmic history. It's a vertical timeline. Lines on the left bluer wavelengths represent closer, more recent gas, while lines stretching far to the right, redder wavelengths, represent gas from the ancient, early universe. By meticulously cataloging every single one of these lines, astronomers can perform an extraordinary feat of cosmic cartography. They can reconstruct a precise, one-dimensional core sample of the universe's large-scale structure along that single, narrow line of sight to the quasar. It's like lowering a geological drill core into the Earth to see the layers of rock, but instead we're drilling a line through the cosmic web, sampling the density of hydrogen gas at every point along the way. A single spectrum gives us a solitary straw's worth of data, but by observing thousands of quasars spread across the sky, we can build up a stunning three-dimensional tomographic map of the universe's hidden matter. We can see how the gas is distributed not as a smooth haze, but in an intricate web-like network of filaments and voids, exactly as predicted by our models of dark matter's gravitational influence. Furthermore, because the light from more distant quasars has been traveling longer, it allows us to see the Lyman alpha forest as it existed further back in time. This lets us study the evolution of the cosmic web itself. We can observe how the forest changes over billions of years, watching as the once smoother distribution of gas in the early universe gradually collapses under gravity into the sharper, more defined filaments we see in the relatively recent cosmos. By measuring the density and clustering of these absorption lines across different cosmic epochs, we can literally take a census of the baryonic content of the universe throughout its history. The Lyman alpha forest doesn't just show us where the missing matter is, it shows us how it has been moving and assembling over time, providing a dynamic, living map of the universe's hidden skeleton, and confirming that these vast reservoirs of diffuse hydrogen contain a massive portion of the atoms we've been searching for all along. While the cosmic web and the Lyman alpha forest reveal matter on the largest scales, some of the most compelling clues come from studying the motion of individual galaxies themselves, specifically how they spin. This brings us to a phenomenon that is foundational to modern astronomy and provides a unique double insight: galaxy rotation curves. Most famously, these curves provided the first strong evidence for the existence of dark matter. But if we listen closely, they also have something very important to tell us about the amount of ordinary matter a galaxy contains, and it's often less than we'd expect. To understand what a rotation curve is, picture a spinning spiral galaxy like our own Milky Way. It's not a solid object like a record on a turntable. It's a vast collection of billions of stars and clouds of gas all orbiting the galactic center. According to the basic laws of gravity as laid out by Kepler and Newton, stars closer to the center of a gravitational system should orbit much faster than those far out on the edges. We see this perfectly in our own solar system. Mercury zips around the Sun at a blistering pace, while Neptune plods along in its slow, stately orbit. For a galaxy, if its mass were concentrated entirely in the visible stars and gas we can see, we should see a very specific pattern in the orbital speeds of its stars, a rapid rise in velocity close to the bright center, followed by a steady and pronounced decline in speed for the stars located in the dimmer outer regions. But in the 1970s, astronomers like Vera Rubin made a landmark discovery that defied this expectation. When they measured the orbital velocities of stars and gas clouds across numerous spiral galaxies, they found something astonishing. The rotation curve did not fall off. Instead of slowing down, the stars and gas in the outer reaches of galaxies were moving just as fast as those near the center. This was completely unexpected. The only plausible explanation was that there had to be a huge amount of invisible mass of dark matter forming an enormous spherical halo around each galaxy, whose gravity was pulling on the outer stars and keeping them from flying off into space. This dark matter halo provides the extra gravitational glue that explains the high orbital speeds. But to calculate just how much dark matter is needed, astronomers first have to account for all the normal matter present. This is where rotation curves give us our 10th clue in the hunt for missing baryons. To model the expected rotation from gravity alone, scientists must first create a detailed inventory of all the luminous mass within a galaxy. They use the galaxy's brightness to estimate the total mass of its stars, and they use radio telescopes to map the vast reservoirs of cold hydrogen gas that often extend far beyond the visible stellar disk. They add it all up to get the total baryonic mass profile of the galaxy. Only then can they calculate the rotation curve that this visible mass should produce through its gravity alone. And consistently, that calculated curve is far weaker than what is actually observed. The shortfall is the evidence for dark matter. However, this process relies on an accurate count of the baryons. If we were somehow underestimating the amount of ordinary matter, if, for instance, there were massive amounts of faint stars or cool gas we couldn't detect, then the need for dark matter would be lessened. Yet, even after meticulously accounting for every star and every atom of gas we can possibly see, the rotation curves still demand a huge amount of dark matter to explain the motion. This tells us two things with great certainty. First, dark matter is undeniably real, and second, the inventory of normal matter within the galaxy itself is complete. We are not missing a significant amount of baryons within the galactic disk itself. The baryons that are supposed to be there according to the Big Bang are not hiding inside the galaxies. This finding powerfully funnels the search outward, away from the bright galactic centers and into the vast intergalactic medium and the extended halos around galaxies, confirming that the missing atoms must reside in those far more diffuse and elusive regions. The rotation curves act like a cosmic scale, weighing both what we see and what we cannot, and the balance always tips toward the invisible. While the rotation of galaxies gives us a one-dimensional measure of mass, there's an even more powerful and direct way to literally see the gravitational fingerprint of matter, whether it's dark or ordinary. This technique relies on one of the most dramatic predictions of Einstein's theory of general relativity. The fact that gravity doesn't just pull on objects, it warps the very fabric of space and time itself. A massive object, like a galaxy or a cluster of galaxies, creates a kind of dimple in space-time. When light from a more distant object travels through this warped region, its path is bent, much like a marble rolling across a stretched rubber sheet would curve around a heavy weight placed in the center. This phenomenon is called gravitational lensing, and it acts as nature's ultimate scale, allowing us to weigh cosmic structures with incredible precision. Gravitational lensing comes in two primary forms, each offering a different level of detail. Strong lensing occurs when the foreground object is extremely massive and perfectly aligned with the distant background object and our line of sight. The result is nothing short of spectacular. The background galaxy isn't just slightly distorted. It can be stretched and magnified into multiple images, bright arcs, or even a complete Einstein ring, a perfect circle of light surrounding the foreground lens. These are some of the most striking images in all of astronomy, and they provide a very clear and direct measurement of the total mass within the lensing object. Strong lensing is like using a cosmic magnifying glass that not only bends the light but also tells us exactly how heavy the lens is. For mapping the broader, more diffuse structures of the cosmic web, astronomers rely on weak gravitational lensing. This is a far more subtle effect. Instead of creating multiple images or rings, the gravity of a large-scale structure, like a vast filament of dark matter, causes a coherent, tiny distortion in the shapes of thousands of background galaxies behind it. Individually, each galaxy's distortion is imperceptible, but statistically, across a huge field of view, a clear pattern emerges. The faint background galaxies appear to be ever so slightly stretched and aligned in a direction tangential to the foreground mass. It's like looking at a distant street lamp through the rippling heat haze rising from a hot road. The image shimmers and warps, revealing the presence of the invisible heat. By meticulously measuring the shapes and orientations of millions of galaxies in large sky surveys, sophisticated computer algorithms can reconstruct a detailed map of the total mass, both visible and invisible, that lies between them and us. This technique has been used to create some of the most comprehensive maps of the dark matter cosmic web ever made. But here is where this powerful tool becomes a crucial clue in our specific search. These weak and strong lensing surveys give us the most accurate measurement possible of the total mass in a given region of space. We know from other evidence, like the cosmic microwave background, what fraction of that total mass should be ordinary baryonic matter and what fraction should be dark matter. The lensing map gives us the sum, and we know the ratio. So, by subtracting the dark matter component, researchers can perform a kind of cosmic accounting, inferring the amount and location of the baryonic mass that must be present, even if it's completely dark and emitting no light of its own. When they do this, they consistently find that the amount of baryons they can directly see in the form of stars and glowing gas is far less than what the gravitational lensing map says should be there. The gravity doesn't lie. There is a significant amount of ordinary matter whose gravitational pull is being felt, contributing to the bending of light, but which remains invisible to our traditional telescopes. This missing baryonic mass isn't missing at all. Its gravitational signature is clearly etched into the distorted light of distant galaxies. It is confirming that the atoms are indeed out there, woven into the cosmic web, their presence revealed not by their light, but by their unmistakable and irresistible pull on the fabric of the universe itself. But to trace the hidden highways of the universe, we sometimes need to follow the journey of its most intrepid explorers, cosmic rays. These are not rays of light, but rather atomic nuclei, primarily protons, that have been accelerated to almost the speed of light by some of the most violent events in the cosmos: supernova explosions, merging neutron stars, or the vicious jets erupting from supermassive black holes. Once launched, these subatomic bullets embark on an epic voyage, streaking across the galaxy and even into the vast intergalactic voids. Their journey, however, is anything but a straight shot. As they travel, they must navigate a complex, invisible landscape of magnetic fields and tenuous gas that fills the space between stars and galaxies. This is where their story becomes a vital clue in our search. The path of a cosmic ray is more like a frantic pinball game than a serene voyage. The magnetic fields woven through the interstellar and intergalactic medium act like countless tiny bumpers, deflecting the electrically charged particles and causing them to scatter and spiral in a chaotic, zigzagging path. This process of diffusion makes it incredibly difficult to ever trace a cosmic ray back to its original source. But crucially, the efficiency of this scattering doesn't just depend on the magnetic fields. It is also profoundly influenced by the density of the ambient gas itself. The more atoms a cosmic ray encounters on its journey, the more densely packed the pinball machine's bumpers are, the more it will be slowed down and its direction randomized. By carefully observing the cosmic rays that finally reach our detectors here on Earth, scientists can perform a kind of cosmic forensics. They can analyze the energy spectrum of these particles and their distribution across the sky. Certain features in this data, like a specific drop-off in the number of particles at very high energies, can tell a story about the total amount of material those particles have had to travel through before reaching us. It's analogous to listening to the sound of rain on a roof. A gentle, steady patter might suggest a light drizzle with little between you and the clouds, while a muffled, diffuse sound would indicate a thick layer of insulation, like a heavy attic absorbing and scattering the noise. In the same way, the sound of the cosmic rays arriving at Earth contains encoded information about the density of the material they've traveled through. This method provides a unique and indirect probe of baryonic matter, particularly in regions of space that are far too diffuse to be seen by any telescope. While it doesn't provide a clean, sharp image like a map of the Lyman Alpha forest, it offers a statistical average, a measure of the overall fogginess of the galactic and intergalactic environment. When these measurements are combined with other techniques, they help to paint a more complete picture, confirming that the spaces between the stars are not empty, but are indeed filled with a pervasive, thin haze of atomic and ionized gas, another crucial piece of the missing matter puzzle, revealed not by its light, but by the way it scatters the universe's fastest travelers. While our search has taken us deep into the vast spaces between galaxies, some of the missing matter might be hiding much closer to home, lingering right in a galaxy's own backyard. This brings us to the extended, faint envelopes of hot gas that are predicted to surround galaxies like our own Milky Way, a region astronomers call the circumgalactic medium, or CGM. Think of it not as a galaxy's atmosphere, but as its entire metropolitan area, a sprawling, dynamic halo of gas that extends for hundreds of thousands of light years, far beyond the bright, familiar stellar disk we see in images. This vast reservoir is a cosmic crossroads, a place of constant activity where gas flows in from the intergalactic medium to fuel future star formation, and where gas is violently ejected back out by the furious winds from supernova and supermassive black holes. It's a chaotic and complex system, and a prime suspect for harboring a significant stash of missing baryons. Finding this gas, however, is a monumental challenge. The circumgalactic medium is astonishingly diffuse. A cubic centimeter of this space might contain only a single atom, making it a far better vacuum than anything we can create in laboratories on Earth. But its immense volume means that all those lonely atoms add up to a staggering total mass. The problem is, gas this thin doesn't glow brightly enough for us to see directly. So, just as with the wider cosmic web, astronomers must again become detectives, using brilliant background sources to hunt for its subtle fingerprints. They point the Hubble Space Telescope and other powerful observatories at distant quasars whose light happens to pass through the CGM of a nearer galaxy. By analyzing the quasar's spectrum, they can search for the specific absorption lines of elements like oxygen and nitrogen that have been highly ionized by intense heat, a clear signpost of million-degree gas. These observations have been successful, confirming that massive halos of hot gas do indeed exist. Around our own Milky Way, for instance, the Chandra X-ray Observatory has detected a massive, shimmering atmosphere of superheated plasma that extends for many times the diameter of our galactic disk. Similar halos have been found around other galaxies. The pressing question now is one of accounting. Is there enough gas in these halos to make a real dent in the missing baryon problem? Current estimates suggest that the circumgalactic medium around a typical large galaxy might contain as much mass as all the stars within that galaxy itself, a truly enormous amount of material. But when you tally it up across the entire universe, it still may only account for a portion of the missing budget, perhaps 10 to 20%. This makes it a crucial piece of the puzzle, but likely not the sole solution. The research is incredibly active, with new telescopes and techniques continually refining our measurements of the density, temperature, and total mass of these elusive galactic halos, inching us closer to understanding their true role in the cosmic inventory. For galaxies, it turns out that the very engines of their creation are also the architects of their dispersal. Across the cosmos, two of the most violent and energetic phenomena imaginable are constantly at work, not just building galactic structures but also tearing them apart in a process that is fundamental to the missing Baryon mystery. This is the concept of astrophysical feedback, and it represents a powerful clue in our search. At its heart, feedback is a story of cosmic recycling on an epic scale, driven by supernova explosions and the furious activity of supermassive black holes. Let's start with the stellar life cycle. Massive stars live fast and die young, ending their brief lives in cataclysmic supernova explosions. A single one of these events can, for a brief moment, outshine its entire host galaxy. But the true impact isn't just the incredible flash of light. It's the immense shockwave of energy and newly forged heavy elements that gets blasted outward at thousands of kilometers per second. This is a galaxy-scale hurricane, a powerful wind that slams into the surrounding clouds of cold gas, the very raw material for future stars. This violent interaction does two crucial things. First, it can compress some of that gas, triggering the birth of new stars. But second, and perhaps more importantly for our story, it can also heat vast quantities of that same gas to extreme temperatures and push it right out of the galaxy's gravitational grasp entirely. Now amplify that effect by a factor of 1 billion, and you get the other primary driver of feedback, active galactic nuclei, or a GN. At the core of most large galaxies sits a supermassive black hole. When a tremendous amount of gas and dust falls into the accretion disk around this black hole, the incredible friction heats the material to millions of degrees, causing it to glow brilliantly and become a quasar. But not all the infalling material is swallowed. A significant fraction of it can be focused and channeled by the black hole's powerful magnetic fields into two opposing, narrow jets of plasma that scream outward at nearly the speed of light. These jets can travel for millions of light years, plowing into the galaxy's gas reservoir and the surrounding intergalactic medium with unimaginable force. This feedback process creates a fascinating self-regulating cycle, a kind of cosmic thermostat. If too much gas falls into a galaxy, it fuels rapid star formation and feeds the central black hole. The resulting supernova and a GN activity then become extremely powerful, blowing huge amounts of that gas back out into the vast halos and filaments, effectively shutting down the feast and preventing the galaxy from growing too large too quickly. This cycle of inflow and outflow ensures that galaxies don't use up all their fuel at once. It's a primary reason why galaxies have the sizes and shapes they do, and why the universe isn't just filled with impossibly enormous ancient galaxies. But for our search for missing baryons, this process is absolutely critical. All that gas being violently ejected from galaxies doesn't just vanish. It is heated to the precise temperatures of the warm-hot intergalactic medium, millions of degrees, and injected directly into the corridors of the cosmic web. This is a massive, ongoing delivery service, constantly transporting ordinary matter from the bright, visible realms of galaxies into the dark, diffuse voids where it becomes nearly impossible to detect. Supernova and a GN are not just spectacular cosmic fireworks. They are the universe's primary distribution system for its missing atoms, constantly pumping baryons out of the easy-to-see galactic disks and into the hard-to-find intergalactic reservoir. They provide the mechanism that solves the how, explaining the journey these atoms took to become lost in the first place. To truly understand the distribution of matter throughout cosmic history, we must journey back to one of the most transformative and dramatic periods the universe has ever experienced, the epoch of reionization. For hundreds of millions of years after the Big Bang, the cosmos was a profoundly dark and simple place. It was filled with a thick, silent fog of neutral hydrogen gas, the remnants of the primordial plasma that had cooled and settled after recombination. This era, aptly named the Cosmic Dark Ages, was a time when no stars shone and no galaxies glittered. The universe was a vast, opaque expanse waiting for a spark. That spark finally arrived with the gravitational collapse of the first structures. Within the densest knots of the dark matter web, the first clumps of gas began to cool and condense, igniting the very first population of stars. These were not like the stars we know today. Theorists call them population 3 stars, and they were behemoths hundreds of times more massive than our Sun, burning ferociously hot and brilliant blue, and living short, violent lives that ended in spectacular supernova. Alongside them, the first black holes began to form and feast. The emergence of these objects marked the beginning of the cosmic dawn, and it initiated a process that would fundamentally alter the nature of the entire universe: reionization. The key to this great transformation was ultraviolet light. The first massive stars and early quasars flooded the cosmos with an incredible torrent of high-energy ultraviolet photons. This radiation is incredibly potent. When a UV photon strikes a neutral hydrogen atom, it has enough energy to rip the electron right off the proton, reionizing the atom and returning it to the plasma state it was in before recombination. Think of it as a cosmic scale thaw, where the frozen neutral atoms are melted back into a hot, ionized gas. But this wasn't a gentle process. It was a relentless frontal assault on the cosmic fog. These first light sources acted like countless ultraviolet lasers, slowly burning a network of ever-expanding, transparent bubbles into the opaque neutral medium. Over several 100 million years, these bubbles grew, overlapped, and eventually merged until the entire universe was once again filled with ionized plasma, a state it has remained in ever since. This epic event is our 15th clue because it acts as a stringent test on the total amount of baryonic matter present in the early universe. The physics is beautifully straightforward. To reionize all the hydrogen in the cosmos, you need a specific number of high-energy photons. It's a simple accounting of energy. You need enough ultraviolet photons to hit enough hydrogen atoms. This means the process required a certain minimum population of those first stars and galaxies to produce that critical radiation budget. If there had been significantly fewer baryons available, less gas to collapse into those first luminous objects, the epoch of reionization would have started later, progressed more slowly, or perhaps even failed to complete altogether. By studying this era, astronomers can work backwards to constrain the baryon count. They use powerful telescopes like Hubble and the James Webb Space Telescope to peer back to the very edge of this epoch, searching for the most distant, faint galaxies. They measure how many there are, how bright they are, and how quickly they ionize their surroundings. When they run the numbers, the results are clear. To explain the relatively rapid completion of reionization, there had to be a substantial amount of baryonic matter already in place at that early time, ready to form stars and black holes. The evidence etched into the ionization state of the universe itself tells us that the total budget of ordinary matter predicted by Big Bang Nucleosynthesis had to have been present. It wasn't missing back then. It was all there, busy doing the fundamental work of lighting up the cosmos. This forces us to conclude that the baryons went missing after this period, likely driven out of galaxies by the very feedback processes that reionization began, scattering them into the vast intergalactic medium where they have remained hidden for billions of years. While the light of the cosmic microwave background gives us a baby picture of the universe's temperature, it also holds a far more subtle and intricate secret within it. A hidden pattern of polarization that acts like a frozen in-time record of the universe's final moments as an opaque plasma. This is our 16th clue, and it offers a uniquely direct window into the conditions of the cosmos just moments before it became transparent. To understand how, we need to picture the universe 380,000 years after the Big Bang. It wasn't a serene, quiet place. It was a roiling, turbulent sea of electrons and atomic nuclei. constantly buffeted by powerful sound waves, those same baryon acoustic oscillations that would later imprint themselves on the galaxies. In this hot, dense plasma, light was not traveling freely. Photons were constantly bouncing off free electrons in a frantic pinball game, a process known as Thomson scattering. Now here is the crucial detail. When a photon scatters off an electron, the interaction can polarize the light, meaning it causes the light waves to vibrate in a preferred direction. Normally, in a perfectly uniform and static soup, all these random scatterings would cancel each other out, resulting in no net polarization. But our early universe was anything but static. It was ringing like a bell with those powerful sound waves. In the regions where the plasma was compressed by a sound wave, the density and temperature were higher. In the rarefied regions between them, the density was lower. This made all the difference. In the high-density regions, the frantic scattering was even more intense, but the light from these hot, compressed areas had a harder time escaping. The last scattering events for photons tended to happen more frequently in the medium-density regions, right at the boundaries between the compression and rarefaction zones. It was in these specific, dynamic environments that the scattering produced a coherent net polarization. The pattern of this polarization on the sky is not random. It is directly tied to the motion of the plasma at the moment of last scattering. It effectively maps the velocity fields of the universe's final shuddering vibrations. Scientists categorize this polarization into two distinct types, which they call E modes and B modes, names borrowed from the similar way electric and magnetic fields behave. The E-mode pattern is a curl-free, radial pattern, much like the electric field around a charged particle. This is the primary type of polarization generated by the density and velocity fluctuations in the primordial plasma itself. And this is where the baryons come in. The strength and specific characteristics of these E-mode patterns are exquisitely sensitive to the amount of baryonic matter that was present. Why? Because baryons are heavy, the dark matter being effectively collisionless, simply sloshed back and forth under gravity. But the baryons, the ordinary matter, had weight and pressure. Their presence in the plasma influenced the gravitational collapse of the sound waves and affected how photons pushed against them. More baryons meant a heavier fluid, which changed the dynamics of those primordial sound waves, altering their speed and amplitude. This, in turn, left a distinct imprint on the statistical properties of the polarization patterns we observe. By creating incredibly detailed, all-sky maps of the CMB's polarization, a monumental task undertaken by observatories like the Planck satellite and the South Pole Telescope, cosmologists can perform a high-precision analysis of these E-modes. They can measure subtle correlations and anti-correlations in the patterns at different angular scales on the sky. The resulting data provides yet another completely independent and incredibly precise measurement of the cosmic baryon density at that very early epoch. The number it gives us is a perfect match. It aligns beautifully with the prediction from Big Bang Nucleosynthesis and the measurement from baryon acoustic oscillations. This is a profound consistency check. It tells us that the total amount of ordinary matter was definitively known and in place just 380,000 years after the Big Bang. The polarization of the cosmic microwave background acts as a cosmic seal, verifying the initial baryon budget. It confirms that the matter wasn't missing at the beginning. It was all present and accounted for. This powerful clue funnels the mystery away from the universe's origins and firmly into its subsequent evolution, telling us that the story of the missing baryons is a story of where this matter journeyed and how it was transformed and hidden over the ensuing 13 billion years. We've seen how observational clues, from the subtle distortions of gravitational lensing to the ancient fingerprints in the cosmic microwave background, all point toward a universe where ordinary matter is not where we thought it was. But what if we could run the ultimate cosmic experiment? What if we could recreate the entire universe inside a supercomputer, set the known laws of physics in motion, and simply fast forward 13 billion years to see where all the baryons should have ended up. This is precisely the power of our 17th clue, cosmological simulations. Even the most massive structures in the universe, the great cities of galaxies known as clusters, hold a paradoxical secret that points directly to our missing matter. These clusters are colossal, containing hundreds or even thousands of individual galaxies all bound together by gravity, but the galaxies themselves are merely the visible landmarks. The real bulk of the cluster's ordinary matter is found in the space between them, a vast sea of superheated gas known as the intracluster medium. This gas is so incredibly hot, reaching temperatures of tens of millions of degrees, that it glows not in visible light but in powerful X-rays. For a long time, astronomers looking at these X-ray emissions thought they understood the life cycle of this plasma. The logic was straightforward and seemed unassailable. The gas is very hot, but it is also incredibly dense by intergalactic standards. All that hot, dense gas should be radiating away its tremendous energy at a ferocious rate, cooling down over time. As it cooled, the laws of physics dictated that it should lose pressure and begin to flow inward, sinking gently toward the cluster's heart in what theorists termed a cooling flow. This steady rain of cooling gas was predicted to be the primary fuel source for rampant star formation at the center of these clusters, potentially creating thousands of new stars every single year. It was a beautiful, elegant, and completely wrong theory. Observations from X-ray telescopes like Chandra and XMM Newton revealed a startling contradiction. When astronomers looked, they simply did not see the evidence for these massive cooling flows. The central galaxies in these clusters were not forming stars at the incredible rates predicted. The gas simply wasn't cooling down as much or as fast as the models said it should. This was the cooling flow problem, a major puzzle that suggested something fundamental was missing from our understanding. The intracluster gas wasn't behaving passively, it was being actively managed. Something was providing a colossal input of energy, reheating the gas and preventing it from cooling and collapsing. It was as if a cosmic furnace kept switching on to maintain the temperature of a vast ocean, counteracting its natural tendency to cool. This discovery was a crucial clue because that intracluster medium represents one of the single largest reservoirs of ordinary baryons in the entire universe. To understand why it remains hot and diffuse is to understand why such a huge portion of the universe's normal matter stays hidden from our view. The solution to this puzzle appears to lie once again with the most energetic engines in the cosmos, active galactic nuclei. At the very center of nearly every massive galaxy cluster sits a giant elliptical galaxy, and within that galaxy lurks a supermassive black hole of almost unimaginable size. While often quiet, these black holes can occasionally become active, pulling in vast quantities of the surrounding hot gas. But unlike the coherent jets seen in quasars, this feeding process is often messy and unstable. It results in what astronomers call mechanical feedback. The black hole doesn't just radiate energy, it erupts. It sends out tremendous bubbles of ultra-hot plasma, inflated by its powerful magnetic fields and jets, which buoyantly rise through the dense intracluster medium like bubbles in a pot of thick soup. These bubbles, which can be hundreds of thousands of light years across, are clearly visible in detailed X-ray images as vast, dark cavities in the glowing gas. As they rise and expand, they push the intracluster gas aside, creating powerful sound waves and shock fronts that travel through the cluster, distributing their immense energy over enormous volumes. This process is incredibly efficient at heating the gas, not through radiation, but through direct mechanical force like a spoon stirring and heating a cup of coffee by stirring it vigorously. This AGN feedback creates a beautifully balanced, self-regulating thermostat. When the intracluster gas is dense and cools rapidly, it flows toward the center and provides more fuel for the central black hole. The black hole responds by becoming more active, erupting with greater ferocity and pumping more energy back into the gas. This reheating shuts off the fuel supply, causing the black hole to quiet down again, allowing the gas to once again begin its slow cooling process, and the cycle repeats over hundreds of millions of years. The result is that a huge fraction of the universe's baryons, all that normal matter contained in the intracluster medium, is maintained in a hot, diffuse, and difficult-to-observe state. The cooling flow problem, therefore, transforms from a puzzle into a revelation. It's not a problem at all, but rather a key mechanism. AGN feedback is the physical process that actively prevents this enormous reservoir of baryons from cooling down, collapsing, and turning into bright, easily visible stars. It is a primary reason why such a vast quantity of the universe's ordinary matter remains hidden in plain sight, suspended as a hot, X-ray glowing fog within the deepest gravitational wells of the cosmos. Perhaps the most unexpected tool in this cosmic investigation comes not from the subtle distortions of ancient light, but from the most energetic and enigmatic signals in the modern universe, fast radio bursts or FRBs. These events are among the most puzzling phenomena ever detected. For just a few thousandths of a second, a source somewhere in the depths of space unleashes a torrent of radio waves, releasing as much energy as the sun puts out in 80 years, all compressed into a blinding flash. Their origins are still debated, linked to incredibly powerful events like magnetars, highly magnetized neutron stars, or perhaps other exotic physics we don't yet fully understand. But for cosmologists, the true value of an FRB isn't necessarily in what causes it, but in the incredible journey its signal takes to reach us. Each burst is a messenger, and the story it tells on arrival is a detailed log of every bit of material it encountered along the way. As this powerful pulse of radio waves travels across millions or even billions of light years, it doesn't move through a perfect vacuum. It slices through the vast, invisible structures of the cosmic web, through the halos of galaxies and the tenuous filaments of the warm, hot intergalactic medium. And in that journey, it interacts with the most fundamental component of that ionized gas, free-floating electrons. This interaction is the key to everything. Radio waves of different frequencies travel at slightly different speeds through a plasma. The higher frequency waves, with their shorter wavelengths, zip through a little faster, while the lower frequency waves lag behind. This effect is called dispersion, and it's a bit like how a prism separates white light into a rainbow, but here it's stretching the radio signal out over time. When astronomers capture an FRB, they don't just see a single spike on their instruments. They see a signal that has been smeared out. The highest frequencies arrive first, followed by a descending chirp of lower and lower frequencies. The degree of this smearing, the total amount of delay between the highest and lowest frequencies, is directly proportional to the number of free electrons the signal passed through on its way to Earth. It's a precise measurement. By analyzing this dispersion sweep, scientists can calculate the total column density of electrons along that specific line of sight, a single laser straight core sample of the universe's invisible material. A single FRB gives us one valuable data point, but the real power emerges when we have a catalog of them, flashing from different distances and in different directions across the sky. Each burst acts as an independent probe, taking the measure of the cosmic electron content along its unique path. By comparing the dispersion from a very distant FRB to that of a closer one, astronomers can effectively peel apart the layers of the universe. They can determine how much of the total electron content comes from our own Milky Way's halo, how much comes from the intergalactic medium, and how much might be associated with the host galaxy of the burst itself. When they add up the contributions from all these individual paths, they are conducting a direct census of the ionized baryons throughout cosmic space. The early results from this new technique are nothing short of revolutionary. The total amount of diffuse, ionized material measured by FRB dispersion aligns strikingly well with the predictions for the missing baryons, providing some of the most direct and compelling evidence yet that the warm-hot intergalactic medium is real, it is massive, and it is the solution to a mystery that has persisted for generations. These mysterious flashes, whose origins we are still striving to understand, have become one of our most powerful torches, finally illuminating the dark matter of the cosmos. This ability to take a precise measurement from a split-second cosmic flash hinges on a specific and beautifully reliable property of physics, the interaction between radio waves and free electrons. The concept is known as dispersion. When a pulse of radio emission, like that from a fast radio burst, travels through any region of space that isn't a perfect vacuum, meaning it contains even a sparse population of free electrons, the different frequencies within that pulse begin to travel at slightly different speeds. Think of it like a group of runners starting a race together but encountering a stretch of mud. The lighter, faster runners in high-top sneakers, representing the higher frequency radio waves, might slog through with only a little slowdown. But the heavier runners in flat shoes, representing the lower frequency waves, get bogged down much more significantly, their feet sticking in the mud with every step. In the plasma of space, the mud is the sea of free electrons, and it affects lower frequency light far more than higher frequency light. The result is that the pristine, sharp spike of the original burst gets stretched out during its long journey. By the time it reaches our radio telescopes, what we detect is not an instant pulse, but a distinctive sweep, a descending chirp where the highest frequencies arrive at our detectors a fraction of a second before the lowest frequencies. The technical term for the total amount of this delay is the dispersion measure, or DM for short. It's a single number calculated by measuring the precise arrival time difference between the highest and lowest frequencies in the signal. And this number is incredibly powerful because it is directly proportional to the total number of free electrons the signal encountered along its entire path. It's a direct tally. A higher DM means the burst passed through more stuff. A lower DM means its journey was through a more empty region of space. A single DM measurement from one FRB is fascinating, but it's like having a single core sample from one random location on Earth. It tells you about that specific spot, but not about the entire planet. The true cosmological power of this tool is unlocked only when we can determine the distance to the burst. Fortunately, when an FRB is detected, large networks of radio telescopes can often pinpoint its location on the sky with incredible accuracy. This allows optical telescopes like the Hubble or large ground-based observatories to then swing into action and image that precise spot, searching for a host galaxy. When they find it, they can measure its redshift, which gives us the distance. Now we have a crucial data pair, a dispersion measure and a redshift. This is where the magic happens. By building a catalog of dozens and eventually hundreds of these FRB events, each with a known DM and a known redshift, astronomers can construct a powerful graph. On one axis, they plot the redshift, which is a measure of distance and look-back time. On the other axis, they plot the dispersion measure. This creates a curve, the DM redshift relation. This curve is effectively a history book. It describes how the total amount of ionized material between us and any given point in the universe has changed over billions of years. A burst from a relatively nearby galaxy will have a lower DM, telling us about the total electron content in the more recent local universe. A burst from an incredibly distant galaxy, whose light has been traveling for billions of years, will have a very high DM, providing a core sample that integrates the electron density all the way back to the early cosmos. By modeling this curve, scientists can separate the various contributors to the total dispersion. They can account for the contribution from our own Milky Way galaxy's interstellar medium and halo, and even estimate the contribution from the FRB's host galaxy itself. What remains is the contribution from the intergalactic medium. the diffuse plasma that fills the cosmic web. This allows for a direct physical measurement of the average density of ionized baryons throughout the vast expanses of space between galaxies. The results from these pioneering studies are already yielding spectacular insights, confirming that the cumulative density of this ionized material is significant and aligns beautifully with predictions for the missing baryons. Each new FRB detected adds another precise date to point to this cosmic census, sharpening our view and bringing us closer than ever to declaring the case of the missing baryons at long last closed. And this brings us to a fascinating intersection of cosmic mysteries, where the case of the missing baryons collides with another famous puzzle known as the missing satellites problem. For years, our most sophisticated computer simulations of cosmic structure formation have presented us with a curious discrepancy. The models, which do an excellent job of predicting the large-scale cosmic web, also tell us that our Milky Way galaxy should be surrounded by a vast swarm of hundreds, if not thousands, of small, dark dwarf satellite galaxies. These satellites are the leftover building blocks of galactic construction, the small protogalactic fragments that merge to form our larger galaxy. Yet, when we look around our local galactic neighborhood, we only observe a few dozen of these faint satellites. So where are all the rest? It's as if we've found the foundations of a city but are missing the vast suburbs that should surround it. The leading theory to explain this discrepancy points directly to the violent astrophysical feedback we discussed earlier, but with a crucial twist that involves gravity's weakest links. In the early universe, the first structures to collapse under the gentle tug of dark matter's gravity were these very small protogalactic halos. They were the seeds from which larger galaxies would eventually grow. However, their gravitational pull was incredibly weak. Their potential wells were shallow, meaning it didn't take much energy for material to escape their grasp. Now imagine one of these first-generation stars forming inside such a fragile, small halo. These stars weren't just any stars, they were colossal, short-lived behemoths that exploded as supernova with unimaginable force. Within the deep gravitational well of a large galaxy like the Milky Way, such an explosion would be dramatic, but the galaxy's strong gravity would eventually recapture most of the ejected gas, recycling it for future star formation. But inside a tiny dwarf galaxy halo, the equation was completely different. The energy released by even a single supernova could be catastrophic. It was like setting off a bomb inside a cardboard box. The ferocious blast wave would easily overcome the halo's feeble gravity, violently expelling nearly all of the baryonic gas, the star-forming fuel, out into intergalactic space. This process, known as feedback-induced gas blowout, would effectively sterilize the small halo. With its gas supply gone, it could no longer form stars. What remains is a clump of dark matter, completely dark and invisible to our telescopes because it never got the chance to light up. This elegantly explains why we see far fewer small galaxies than the simulations predict. The dark matter halos are all there, but most of them were stripped of their luminous material before they could truly begin. And this is where the two cosmic mysteries lock together into a single, beautiful solution. All that ordinary matter, all those protons and neutrons that were violently blown out of those countless small halos, where did it go? It didn't just disappear. This ejected gas was heated by the shock waves of its own expulsion and launched into the voids. It became tenuous, hot, and incredibly diffused. In other words, it was transformed into the very substance we've been searching for, the warm, hot intergalactic medium. The same energetic feedback that prevented the formation of thousands of small satellite galaxies around our own Milky Way may have been the primary delivery mechanism that stocked the cosmic web with a significant portion of its missing baryons. One of astronomy's most puzzling absences, the lack of small galaxies, may directly point us toward the location of another, the missing normal matter scattered across the universe by the very first stars to ever explode. Throughout our investigation, we've explored vast cosmic webs and violent galactic feedback, but sometimes the most profound clues are found not in complex structures, but in the simplest of numbers. In the language of cosmology, one number stands apart for its elegant simplicity and its immense power to constrain our theories: the baryon-to-photon ratio, represented by the Greek letter eta. This is not a number derived from complex observations of distant galaxies. It is a fundamental property of the universe, an initial condition set during the very first moments after the Big Bang, and it has remained constant ever since. To understand why this ratio is so crucial, we need to step back and consider the very nature of the early cosmos. In those first few minutes, the universe was an unimaginably dense and hot fireball, a seething plasma of particles and energy. Among the most abundant constituents were photons, the particles of light, and baryons, the protons and neutrons that would later form atomic nuclei. In this frantic environment, the total number of each was essentially fixed. As the universe expanded and cooled at a breathtaking rate, this ratio, the number of baryons for every single photon, became a permanent feature of the cosmos, effectively frozen into the fabric of reality. It is a direct relic, a single number that carries information from a time before the first atoms even formed. We can't go back in time to count these particles ourselves, but we can deduce the value of eta with stunning precision by reading the two clearest historical records we have: Big Bang Nucleosynthesis and the cosmic microwave background. The first record comes from the universe's first 3 minutes. The process of Big Bang Nucleosynthesis, which forged the first hydrogen and helium nuclei, was exquisitely sensitive to how densely packed the universe was with baryons. If there had been too many baryons, nuclear reactions would have proceeded more efficiently, converting nearly all the hydrogen into helium and even creating noticeable amounts of heavier elements like lithium. If there had been too few baryons, the reactions would have been feeble, leaving behind a universe composed almost entirely of hydrogen. The observed primordial abundances of hydrogen, helium, and deuterium, which we can measure in the oldest regions of space, act like a cosmic pressure gauge. They tell us the density of baryons during that brief window, and from that we can calculate the baryon-to-photon ratio. The answer is a very small number, approximately 6.1 times 10 to the negative 10. This means for every billion photons racing through the universe, there are only about 6 baryons. The second, even more precise measurement comes from the cosmic microwave background. The tiny temperature fluctuations imprinted on this ancient light are the frozen sound waves of the infant universe. The characteristics of these waves, their spacing and amplitude, depend directly on the properties of the plasma they were moving through. A key property is the amount of baryonic matter present, as its weight and pressure influenced how these waves oscillated. By creating exquisitely detailed maps of the CMB's temperature and polarization, missions like the Planck satellite have been able to measure the baryon density, and thus the baryon-to-photon ratio, with an uncertainty of less than 1%. The result is a perfect match to the number derived from nucleosynthesis. This is a monumental triumph for the Big Bang theory, confirming our understanding of the universe's earliest moments with incredible accuracy. This is where eta transforms from a successful prediction into our 22nd clue for the missing baryon problem. This number is not a suggestion or an estimate, it is a definitive, observed fact. It tells us with unwavering certainty exactly how many protons and neutrons the universe contained within its observable volume some 13.8 billion years ago. And because the number of baryons is conserved, they are not created or destroyed on cosmic timescales outside of particle-antiparticle annihilation, which is rare. That exact same number of baryons must exist today. There is no wiggle room, no possibility that the initial calculation was wrong. The number is fixed, therefore any complete inventory of the modern universe must account for every single one of them. When our counts of stars, galaxies, and nebulae come up short, the discrepancy isn't a matter of debate. It is a direct violation of a fundamental law of physics as recorded in the universe's oldest archives. The baryon-to-photon ratio is the ultimate accounting ledger, and it states in no uncertain terms that the books must balance. Our job is not to question the number, but to find where the missing entries have been hidden. But the cosmic web is not just a passive sea of hot gas and gravitational forces. It is also threaded with a subtle and invisible architecture of its own. This brings us to a factor that could fundamentally alter our understanding of how the missing baryons behave and why they've been so difficult to find: the presence of magnetic fields. We often think of magnetic fields as localized phenomena, something confined to planets, stars, or the disks of galaxies. But over the past few decades, evidence has been mounting that these fields are far more pervasive, stretching out into the vast and seemingly empty intergalactic medium itself. These are not the powerful, structured fields of a magnetar. They are incredibly faint, perhaps 1,000,000 times weaker than Earth's own magnetic field. Yet, despite their weakness, their sheer scale is unimaginable, permeating filaments of gas that are millions of light-years long. The origin of these intergalactic magnetic fields is a major puzzle in itself. They may have been seeded in the ultra-early universe and then stretched to cosmic proportions by the expansion of space, or they could have been blown out from galaxies over billions of years by those same supernova and quasar winds that distributed the baryons in the first place. Regardless of how they got there, their presence adds a whole new layer of complexity to the physics of the warm-hot intergalactic medium. This isn't just a hot gas, it's a hot magnetized plasma, and that changes everything about its behavior. This field of study is known as magnetohydrodynamics, and it governs how electrically conducting fluids like plasma interact with magnetic fields. One of the most significant effects is on the transport of heat. In an ordinary, unmagnetized gas, heat flows freely from hot regions to cold regions, but magnetic field lines can act like insulators, dramatically reducing this thermal conduction. They can trap heat within certain regions, preventing hot gas from cooling down as efficiently as we might expect. This could be a crucial piece of the puzzle for the cooling flow problem in galaxy clusters, helping to explain why the intracluster medium remains so hot for so long. The magnetic fields might be acting as a cosmic blanket, helping to maintain the high temperature of the gas and keeping it in its diffuse, hard-to-detect state. Furthermore, these fields have a profound impact on the dynamics and structure of the gas itself. The magnetic pressure and tension can provide additional support against gravitational collapse, preventing some regions of the cosmic web from condensing into galaxies and stars. They can channel the flow of gas, directing it along the field lines like cars on a highway, which could explain the filamentary structures we infer from other observations. They also play a crucial role in the propagation of cosmic rays, as we discussed earlier. The chaotic scattering of these high-energy particles is entirely due to their interactions with these invisible magnetic fields. By studying the paths of cosmic rays, we're indirectly mapping out the structure and strength of the magnetic fields that fill the space between galaxies. This means our ability to use cosmic rays as a probe for baryonic density is intrinsically linked to our understanding of these magnetic environments. If our models of the fields are wrong, our estimates of the gas density from cosmic ray data could be significantly off. The challenge, of course, is detection. How do you measure a magnetic field 1,000,000 times weaker than Earth's across a void of empty space? One promising method is through a phenomenon called Faraday rotation. When polarized radio waves from a distant quasar or a fast radio burst pass through a magnetized plasma, the orientation of their polarization slowly rotates. The amount of this rotation depends on the strength of the magnetic field and the density of electrons along the line of sight. By measuring the Faraday rotation from many different sources spread across the sky, astronomers can begin to piece together a three-dimensional map of the magnetic fields woven through the cosmic web. It's a painstaking process, but each new data point helps to constrain the models. Accurately accounting for these magnetohydrodynamic effects is no longer a niche consideration. It is becoming a crucial frontier in our quest to finally solve the missing baryon problem. The invisible magnetic architecture of the universe may be the final key that unlocks the secret of where the atoms have been hiding, revealing how these faint forces shape the largest structures in the cosmos. While our current telescopes have brought us to the brink of solving this cosmic mystery, the final, definitive proof will likely come from the next generation of observatories, instruments so powerful they will transform the warm-hot intergalactic medium from a theoretical prediction into a detailed, observable map. These aren't incremental upgrades, they are monumental leaps in technology designed with the explicit purpose of probing the universe's darkest secrets. Leading this charge is the European Space Agency's Athena mission, the X-ray Observatory for Astrophysics. Imagine a telescope with a collecting area for high-energy light that is 100 times larger than today's best X-ray observatory, Chandra, coupled with a spectrometer so sensitive it can detect the faintest whispers of highly ionized oxygen and nitrogen. Athena is being built to do what has so far been nearly impossible: to see the WHIM not just as a shadow against a brilliant quasar, but to directly image its faint, diffuse glow. It will be able to map the intricate filamentary structure of the cosmic web in X-ray light, tracing the flow of hot gas between galaxy clusters and directly measuring its density and temperature. This will allow us to finally weigh with precision this vast reservoir of matter and confirm once and for all that it contains the full missing budget of baryons. Simultaneously, on the radio side of the spectrum, a truly colossal endeavor is taking shape: the Square Kilometre Array, or SCAR. This isn't a single dish but a revolutionary interferometer, a network of thousands of radio antennas spread across 2 continents in South Africa and Australia, all working in concert to create a collecting area of, as the name implies, a square kilometer. The sheer sensitivity of the SCAR will be unlike anything we've ever had, allowing it to detect fast radio bursts from the very edge of the observable universe at a rate of thousands per day. Where we now have a catalogue of a few hundred, the SCAR will provide millions. This torrent of data will be transformative. Each new FRB will provide a pristine core sample of the ionized content along its path, and with millions of these paths crisscrossing the entire sky, we will be able to construct a stunningly detailed 3-dimensional tomographic map of the baryon distribution throughout cosmic history. It will be like moving from a world of isolated, hand-drawn maps to a live, high-resolution global weather satellite system for the cosmic web, tracking the ebb and flow of ordinary matter with unprecedented clarity. But the revolution doesn't stop there. NASA's upcoming Nancy Grace Roman Space Telescope, with its enormous field of view, will perform massive surveys of the sky to study dark energy. But a key part of that work involves using its powerful vision to measure the subtle distortions of weak gravitational lensing with exquisite detail. This will provide an even more precise map of the total mass distribution, including the gravitational tug of the diffuse baryons against which the other measurements can be compared. Furthermore, the James Webb Space Telescope is already deepening our understanding of the early universe's feedback processes, studying how the first galaxies and quasars ejected their material to begin populating the cosmic web with the very atoms we are now searching for. Together, these observatories represent a coordinated, multi-wavelength assault on the problem. Athena will see the hot gas in X-rays, the SCAR will trace it with radio dispersion, and Roman will weigh its gravity. By combining these independent datasets, we will cross-verify the results, eliminating uncertainties and building an irrefutable case. We are no longer just piecing together clues from whatever tools we have available. We are building the perfect tools for the specific job of finding what has been hidden, bringing the complete story of the universe's ordinary matter into sharper focus than ever before. And so we arrive at our final and perhaps most important clue, one that isn't a single piece of evidence but the very nature of the scientific endeavor itself. After exploring 24 distinct pathways from the primordial predictions of the Big Bang to the fleeting chirps of fast radio bursts, it becomes overwhelmingly clear that no single telescope, no solitary technique, and no lone genius will ever solve the mystery of the missing baryons on their own. The universe is simply too complex, its secrets too well guarded. The ultimate solution will not be a eureka, a moment found in a single dataset, but a consensus built from a symphony of evidence, where each instrument in the cosmic orchestra plays an essential and irreplaceable part. This is the multi-messenger approach, the collaborative, multi-wavelength heart of modern cosmology. Think of it like assembling a global investigation to find a missing treasure. One team uses sonar to map the ocean floor, revealing the general shape of the seabed and the canyons where something might be hidden. This is the role of the cosmic microwave background and gravitational lensing, mapping the large-scale gravitational topography of the universe. Another team employs deep-diving submersibles with powerful lights to explore those specific canyons, capturing detailed images of the terrain. This is the job of X-ray observatories like Chandra and the future Athena, directly probing the hot gas in filaments and clusters. Meanwhile, a fleet of ships drops thousands of sensors into the water, each one recording the time it takes for a sound signal to travel through the water column, building a three-dimensional map of the ocean's density. This is precisely what we do with the dispersion measures from thousands of fast radio bursts. And high above, satellites take infrared and visual images to track currents and temperatures that influence everything below, a role filled by optical and ultraviolet telescopes like Hubble and Webb, studying the galaxies and their feedback processes that distribute the matter in the first place. No single method gives you the whole picture, but together they converge on the truth. This is the powerful elegance of the multi-messenger strategy. Each line of evidence has its own strengths and its own blind spots. X-ray observations can pinpoint hot gas but struggle with its faintest, most diffuse forms. The Lyman alpha forest in quasar spectra is exquisitely sensitive to neutral and mildly ionized hydrogen, but can miss the hottest, most highly ionized plasma that doesn't produce clean absorption lines. Gravitational lensing tells us unequivocally where the mass is, but it cannot distinguish between dark matter and ordinary matter. Fast radio bursts provide a direct measure of total electrons along a line of sight, but require independent distance measurements to be meaningful. And sophisticated computer simulations provide the crucial theoretical framework, testing how well our understanding of physics can recreate the universe we observe, but they always need real-world data to validate their predictions. It is only by weaving all these independent threads together that we can create a tapestry strong enough to hold the answer. When the density of the WHIM measured by FRBs matches the amount of mass inferred by lensing in the same region, which in turn aligns with the predictions of simulations that incorporate AGN feedback, we can finally move from a compelling hypothesis to a settled fact. This grand, collaborative effort is a testament to how science truly operates at its best. It is a global enterprise requiring the expertise of radio astronomers, optical observers, X-ray specialists, theoreticians, and computer modelers, all working in concert, often across international borders and decades of time. The solution to the missing baryon problem is being written not in a single research paper, but in the entire scientific literature, with each new observation adding another verse to the story. It celebrates the power of human curiosity and cooperation, showing that by combining our different ways of seeing the universe, we can illuminate even its darkest corners. The mystery that once seemed so intractable is now on the verge of being solved, not by a single clue, but by the collective weight of all 25, proving that the whole of our understanding is infinitely greater than the sum of its individual parts. So after this incredible journey through 25 clues, what's the final verdict? The story of the missing baryons isn't a tale of something that vanished into nothingness. It's a story of perspective and of our own vision finally catching up to the universe's grand design. We began with the unshakable predictions of Big Bang Nucleosynthesis, a cosmic birth certificate that told us exactly how much normal matter should exist. For decades, that number seemed to taunt us as our inventories of stars and galaxies came up dramatically short. But that initial failure was the spark that ignited a revolution in astronomy, pushing us to develop new tools and new ways of seeing. We learned to stop looking just for the light and start looking for the shadows, the subtle distortions, and the faintest of echoes. We discovered that the dark matter provides the universe's skeletal structure, a cosmic web that guides where everything must go. We found that the violent lives and deaths of stars and black holes don't just create light. They act as cosmic engines, pumping enormous amounts of ordinary matter out of galaxies and into the voids, heating it to millions of degrees and hiding it in a form that's invisible to our traditional eyes. This matter, the warm, hot intergalactic medium, doesn't glow brightly on its own, but we've developed ingenious ways to find it. We use the most distant quasars as cosmic lighthouses, reading their altered spectra like a fingerprint. We study the subtle distortions in the oldest light in the universe, the cosmic microwave background, to see the shadows of these vast, hot filaments. And now, we even use the split-second chirps of mysterious fast radio bursts as precise measuring sticks to take the density of the cosmos. Piece by piece, clue by clue, the evidence has converged. The missing baryons aren't missing at all. They are hiding in plain sight, woven into the very fabric of the cosmic web, residing in those immense, diffuse filaments of hot gas that stretch between the galaxies. The puzzle isn't completely finished. There's still work to be done to precisely weigh every last atom and understand the intricate physics of these vast magnetic environments. But the case is overwhelmingly clear. We are living in a universe where the most ordinary stuff, the atoms that make up you, me, and every star we see, is not primarily in those brilliant points of light. Most of it is out in the dark, in the hot, thin, magnificent architecture that binds the entire cosmos together. It's a humbling and awe-inspiring realization. The next time you look up at a dark, clear night sky, remember, the emptiness is an illusion. You are looking at an ocean of matter, a hidden world of atoms just waiting for our ingenuity to reveal it. This story is still being written, with new chapters arriving from telescopes like the James Webb Space Telescope, the upcoming Athena Observatory, and the Square Kilometre Array. So stay curious, because the universe has shown us that its greatest secrets are often hiding in the most unexpected places, waiting for the right moment to be found.